Hi, welcome back to your second lecture for Chapter 1, Chemistry of Our Lives, Part 2. So in this chapter, we are going to be exploring how we as scientists and chemists measure matter. So in order to do that, we're going to have to learn a few different things. We're going to have to learn how to write a number in scientific notation, how to write the names and abbreviations of the metric and SI units that are commonly used in measuring volume, length, mass, temperature, and time. We'll also learn how to identify a number as a measured or exact value, and then determine the number of significant figures that are shown in a measured number. We'll also learn how to use conversion factors to help us change from one unit to another, and then apply all of these concepts to help us calculate the density of a substance and use the density of a substance to calculate the mass or volume of a substance. We can also use density to identify an unknown substance. Throughout all of this process, we'll also continue getting experience using critical thinking skills to help us evaluate claims and statements. All right, so let's go ahead and get started with talking about the different units of measurement that scientists and chemists employ. So scientists commonly use what's known as the metric system of measurement, and we have adopted a modification of the metric system called the International System of Units as our worldwide standard. That way, whether we're in the United States or the UK or Germany or China or France, all scientists can speak the same language when we are talking about measuring things. This International System of Units, or the SI system, is the official system of measurement used throughout the world to help us define the units of length, volume, mass, temperature, and time. So as we see, our common metric unit for volume is liter, whereas the common SI unit is cubic meters. Conversely, the metric unit of length and SI is both meter. Let me turn on my little pointer, right? So when we think about length, whether we're talking about the metric system or the SI system, it is meter. However, in mass, the SI system uses kilogram, whereas the metric system defines as the base unit gram. In temperature, the metric system uses Celsius, where the SI system uses Kelvin, and then for both systems, we're going to use seconds for time. So again, in thinking about which system we're talking about, whether it's the metric or the SI, we may have to do some conversions. Say if we're dealing with temperature, mass, or length, or volume. So let's get some practice identifying units and the property they represent. So let's go ahead and log into masteringchemistry.com and open the assignment Chemistry 1 or Chapter 1 Chemistry Part 2 in class. And then pause the video and answer questions 1 through 2. Again, feel free to work with a partner if you're working at home or work on your own. So pause here, and then when you're ready, come back and continue the lecture. All right, so now that we've gained some practice in identifying which units are associated with which dimension of measurement and differentiating between the metric system and the SI system, let's now talk about how we capture measurements and define what significant figures are. So measured numbers are the numbers obtained when we measure a quantity such as height, weight, or temperature. So to write a measured number, we must first observe the numerical values that are given to us based on the instrument that we're using. So for example, here we're trying to measure the length of a piece of wood. So the instrument that we are using is a ruler. So first thing we're going to do is observe the numerical value of the marked lines. So here our instrument tells us that the ruler is going to fall between 4 and 5 centimeters. And then we will estimate the value of the number between the mark. So since our mark is every 1 centimeter, we will estimate the next decimal place, which is the 10th value between the centimeters, between 4 and 5. That estimated number is in the final digit in our measured number. So we could guess this is maybe almost halfway between 4 and 5. So I would estimate this as 4.5 centimeters. And that's what I would write down as the measured number for the length of this piece of wood. So we can gain a little more practice in this. As we see, this was the example we had on the last slide. Again, if we guess that this is falling halfway between 4 and 5, we would write down that the length is 4.5. Alternatively, this ruler gives us some more graduated lines here, right? So now we would have to guess the 100th place because we are given markers every 10th place. So now we can see, all right, here's 4.5. It's actually a little more than 4.5. So I would guess, and it's almost 4.6, but not quite 4.6. So I would guess that this, or not guess, I would estimate that this length of wood is 4.55 centimeters versus 4.5 centimeters now that I have a more accurate ruler. Alternatively, if your measured object falls exactly on a graduated line, then you would indicate that it is 3.0. That 0.0 is telling the viewer or the audience that you have confidence in that ruler is exactly at the 3 mark, hence 3.0. So therefore, when we start talking about measured numbers and we start talking about how we are estimating that final digit based on the instrument that we're using, that final digit being whatever number is between the smallest graduated lines, we need to talk about significant figures. So in a measured number, the significant figures are all the digits, including the estimated digit, right? That last digit that's between the 2 graduated lines. Significant figures are used to help represent the amount of error associated with a measurement. So for example, if we go back to our previous slide, right, here this ruler does not give us graduations between each centimeter where ruler B does. So ruler B is going to have less error associated with it because we can more clearly see that the length of this piece of wood is actually slightly over 4.5 centimeters, where we really couldn't estimate that clearly in ruler A. Therefore, if we notice the value difference between A and B, A has 2 significant figures, 4.5, whereas B gives us 3 significant figures, 4.55, meaning we have a higher confidence in the measured value using B versus A. So how do we determine which numbers are significant? Because not all numbers in a measured value are significant. So there's 3 rules we need to keep in mind when we are estimating the number of significant figures. So the first rule, all non-zero digits are significant. So for example, in this value right here, the numbers 5, 8, and 3 are all non-zero digits. Therefore, they are significant. Any zeros in between non-zeros are also considered significant. So this 0 right here is also a significant figure. And then any trailing 0 after a decimal point is also significant. So for example, this 0 right here is also significant. Keep in mind, leading zeros or zeros before the first non-zero number are not significant. So we do not count them as a significant figure. So when we are trying to determine how many significant figures are in this measured value right here, we would start with our first non-zero and count all the way. So 1, 2, 3, 4, and then 5. This 0 is considered significant because it is after the decimal place. So this measured value right here has 5 significant figures. Now, one thing we also want to keep in mind, trailing zeros after a non-zero when the decimal point is not shown are not significant. So for example, if I have a measured value of 100, but there is no decimal place right here after this 0, then we can only conclude that the non-zero 1, right, this 1 right here, is the only significant value. Therefore, 100 has 1 significant value. If we include the decimal place, right, this little period right here after that 0, then these zeros do become significant because now they are considered an in-between 0. And they are, now this number has 3 significant figures. Okay, so again, let's go over the rules. All non-zero digits are significant. So anything that is not a 0 is considered as significant figures. Zeros between non-zeros, such as this 0 between 5 and 8, are also significant. Any trailing zeros after the decimal place, or if a decimal place is shown, are also significant. The only time a trailing 0 is not significant is if there is no decimal place. Okay? All right, so again, keep in mind that's how we are going to determine how many significant figures are in our measured values. So again, if we go back to our previous examples where we were measuring with the ruler, right? A has 2 significant figures, right? Because there's 2 non-zero numbers. B has 3 significant figures because there's 3 non-zero numbers. And C has 2 significant figures, right? Because we have a non-zero and then we have a trailing 0 that is after a decimal place. So 2, 3, 2. Now, sometimes large numbers have zeros between the non-zero and the decimal that are not significant, right? So remember, in this value right here, right, this 100 million, notice that we don't include a decimal place here. So if there's no decimal place included after that last 0, then we would have to assume that all of these zeros coming after the 1 are not significant. So often we can convey that more clearly by using scientific notation. So we could demonstrate that the first digit is the only significant figure by converting 100 million to scientific notation, which is the same thing as saying 1 times 10 to the 8th power. Basically, when we go into scientific notation, what we're doing is we're taking this decimal place that exists right here and we're moving it 1, 2, 3, 4, 5, 6, 7, 8 times. Hence, we're saying that it's 1 times 10 repeated 8 times, right? And if you do that, you'll end up with 100 million. If the first 2 digits are significant, so let's say this first 0 is significant, we do have confidence in that placeholder, then we can include the decimal place and any zeros after that are considered significant. So we can still say 1 times 10 to the 8th, but if that first 0, this right here, is confident, like we know that that is a 0, then we can say 1.0 times 10 to the 8th. If there's 2 places that we are confident in that are zeros, then we could say 1.00 times 10 to the 8th. So this is how scientific notation can kind of help really clarify really, really large numbers that have confidence in multiple place values. So again, to convert to scientific notation or away from scientific notation, we are going to move our decimal place either to the left or to the right. So we can use scientific notation for really large numbers or really small numbers. Okay, so for example, if we want to convert the value 156,000 into scientific notation, we would move our decimal place over 1, 2, 3, 4, 5 times, hence 10 to the 5th, and then convey those other two non-zero numbers as decimal places. So it would be 1.56 times 10 to the 5th. Anytime you move your decimal point to the left, going this way, then your exponent is going to be positive, right? So it's going to be plus 5. Conversely, if we want to convert a very small number into scientific notation, then we would move our decimal place to the right. Whenever we do that, our exponent should have a negative value because we moved into the right. All right, so for this example, we're going to move our decimal place 1, 2, 3, 4, 5, 6 in order to get 5.3 times 10 to the minus 6. Again, because we moved to the right, our exponent goes down, and so it becomes negative 6. We have a couple other examples here. If we wanted to write this value in scientific notation, we move our decimal place over 7 times in order to get 6.5 times 10 to the 7th. And conversely, if we wanted to convert this very, very small decimal, we would move over 9 times in order to get 2 times 10 to the minus 9. Right? And we can go in both directions. We can go from scientific notation to a true number or from a true number to scientific notation. Or not true number, expanded number, I guess. They're both true numbers. Now, all of these that I've just talked about are measured numbers. So when we're thinking about significant figures in scientific notation, often we are talking about measured numbers, or a number that we obtain by using an instrument in order to get length, volume, time, temperature, any of those things. Scientists also use something considered exact numbers. Exact numbers are defined as not measured, and therefore they do not have a limited number of significant figures, right? We're not limited by the instrument, by the ruler or the scale or whatever it is we are trying to obtain that measured number by. Therefore, we often don't have to worry about counting our significant figures or demonstrating them. They are obtained typically by counting. So for example, there's 8 cookies in a jar. They can also be definitions in the same measuring system. Again, usually we think of conversion factors as exact numbers. So for example, there's 12 eggs in a dozen. And they can also be definitions that compare to units, such as 4 cups in 1 quart. And so when we say the one value 4, that 4 cups in 1 quart is also the same as 4.000000 infinite significant figures in 1 quart. So again, an exact number has 0 uncertainty in it. Therefore, it has an infinite number of significant figures. And examples of exact numbers are counted numbers or defined unit conversions, right? So 4 apples, or 100 centimeters in a meter, or 16 ounces in a pound, right? Or counting 8 eggs, right? All of these are considered exact numbers. So let's practice now identifying exact numbers, measured numbers, and the number of significant figures. So return to the in-class assignment on masteringchemistry.com. Complete questions 3 and 4 on your own or work with a partner if you have somebody sitting next to you while you work through this lecture. So pause the video here and then come back when you have finished those questions. All right, so let's talk about calculations with significant figures. So in multiplication or division, the final answer is written so that it has the same number of significant figures as the measurement with the fewest significant figures. So for example, if I am trying to multiply two measured numbers, so 24.66 centimeters times 0.35 centimeters, when I put that into the calculator, I'm going to get the value 8.631. Now, I'm not going to report that, right? Because I also have to convey the confidence in that value using my significant figures. So the rule here is that whichever has the lowest significant figures, that is what you will round your answer to. So the first value, 24.66, has 4 significant figures. And the second value, 0.35, has 2 significant figures. Remember, leading zeros do not count. So only the non-zeros count. Therefore, the answer should be rounded to 2 significant figures. Since 3 is less than 5, we are going to round down to 8.6 centimeters squared. Same thing with whether we are multiplying and dividing or just simply dividing, we're going to use the same rule. So for example, if we have the calculation 21.5 centimeters times 0.30 centimeters divided by 1.88 centimeters, when I plug that into the calculator, I'm going to get the value 3.43085163. Again, I'm not going to write that down as my answer. Instead, I'm going to have to round to the lowest number of significant figures. So I need to analyze each value. So 21.5 is 3. 0.30 is 2, 1.88 is 3. Therefore, my answer is limited to the measured value with the lowest number of sig figs, which is this one here, which is 2. And so I'm going to round my answer to 2 significant figures. And again, remember this one is 2 significant figures. The leading 0 here is not significant. This is my first non-zero integer, so it is significant. And then this 0, because it follows the decimal point after a non-zero, is going to be significant. So we count both of these values. Now, sometimes the calculator display may contain fewer significant figures than needed. Therefore, we would add zeros trailing the number in order to convey that there should be more significant figures than was calculated. Now, when we are adding or subtracting measured values, here the final answer is written so that it has the same decimal place as the measurement with the fewest decimal places. So here we really don't concern ourselves with the significant figures, but we concern ourselves with the decimal place holder. So for example, if we are adding 3 measured values together, 2.012, 61.09, and 3.0, the best thing to do is to align your decimal place so that you can clearly see which one has the smallest or the fewest decimal places. Complete your calculation and then round to the fewest decimal place. So for example, this one has 3 decimal places, this one has 2, this one has 1. Therefore, I'm going to round to the 1 or 10ths decimal place. So 66.1 is the answer that I would report. So again, multiplication and division with measured values, we focus on the total number of significant figures. However, when we are adding or subtracting measured values, we focus on the decimal place and whichever has the fewest decimal places. Okay. All right, so again, another example here. Here we're subtracting, so 65.09 minus 3.0 minus 62.09. Again, align your decimal place, do your calculation, and then round up to the number that has the fewest decimal places. So 3.0 is again limited to the tenths place, and we would round. Oh, I guess my line should be here, right? So it should be 65.09 minus 3.0 equals 62.09, and then I would have to round up to 62.1 in order to convey that we should only go to the tenths place. All right, so again, let's take a break and practice this concept. So practice doing calculations with measured numbers, either multiplication, division, or addition, subtraction, and applying those rules. So let's return to masteringchemistry.com, complete question 5, either on your own or work with a partner if you happen to have one with you. When you're ready, come back to the lecture. All right, so let's talk about metrics prefixes. So the really nice thing about using the metric system is that we can use prefixes in place of sort of the scientific notation. And this can allow us to increase or decrease its size by a factor of 10. So for example, milli and micro are used to make smaller units versus kilo or mega, which is used for larger units. Our base unit, right, such as grams, usually will not have a prefix, and it's what is raised 10 to the 0, or is the base unit. However, if we were talking about kilograms, right, a kilogram represents 1 times 10 to the 3 grams, right? So that's just a nice, so it just represents that your base unit multiplied by this factor 10 to the 3. Conversely, if we're talking about really small numbers such as milligrams or micrograms, we again, if we have the little m, that represents milli, or 10 to the minus 3 grams, or micro, 10 to the minus 6 grams. Now that micro shouldn't be an M, it should be a mu symbol, and we'll talk about that in class. So prefixes and equalities. The relationship of a prefix to a unit can be expressed by replacing the prefix with its numerical value. So for example, when the prefix kilo in kilometer is replaced with its value of 1,000, we find that a kilometer is equal to 1,000 meters, right? So a kilometer is 1,000 meters, or 1 times 10 to the 3 meters. Kiloliter is the same as 1,000 liters, 10 to the 3 liters, and kilogram is 1,000 grams, 10 to the 3 grams. So again, kilo is the constant. It's always going to be equal to 1,000 of that base unit. So 1,000 meters, 1,000 liters, or 1,000 grams. So that's the really nice thing about this metrics prefix system, is that it's universal across all units. So let's practice here filling in the blanks with the current prefix. So 1,000 meters is equal to 1 kilometer, or little km. Now the reason I know that is I can go back to this nice little prefix scale, and I can say 10 to the 3 is the same thing as 1,000, so k, kilo. 1 times 10 to the minus 3 grams is equal to 1 what? Again, let's go back to this scale. 10 to the minus 3 is right here, so that's going to be equal to milligrams, or little m. So I would put a little m right here to represent milligrams. Conversely, 0.01 meters is going to be equal to 1 what? Well, 0.01 is the same thing as 1 times 10 to the 1, 2, minus 2, so that's 10 to the negative 2. Again, I can go back and see 10 to the minus 2 is right here, so centa or C, centimeters. So I could write a little c right here. All right, so this prefix scale will be given to you on your test. So you don't have to memorize centa is 10 to the minus 2 or nano is 10 to the minus 9. But I do want you to learn how to use this scale in order to do these conversions. All right, so let's get some more practice with that. Return to masteringchemistry.com. Complete now questions 6 and 7. And again, feel free to work with a partner. Pause the lecture here, and when you're ready, come back. All right, so let's talk about equalities, or what we probably think of them as conversion factors. So for example, when we're talking about converting in the metric system, those are equalities. So 1 meter is the same thing as 1,000 millimeters. 1 pound is the same thing as 16 ounces, or 2.20 pounds is the same thing as 1 kilogram. So all of these are equalities, and equalities are defined as an item that uses 2 different units to describe the same measured amount. So for example, 2.2 pounds is the same as 1 kilograms. And they are often written for relationships that help us convert between the units of the metric system, the US unit system, or between metric and US system. So between the metric system, right, 1 meter versus millimeters, between metric and US, pound versus ounces, or between US units, sorry, pounds versus ounces, and then between metric and US units, pounds versus kilograms. So any equality can be written as a fraction called the conversion factor. So the equality is this right here. So 1 meter equals 1,000 millimeters, or 1 pound equals 16 ounces. The conversion factor is when we write that equality as a fraction, with 1 value in the numerator and 1 value in the denominator. So for example, in the equality, there are 60 minutes in 1 hour. We can write the conversion factor as 60 minutes over 1 hour, and we can also flip it and write it as 1 hour over 60 minutes. So remember, every equality is going to have 2 conversion factors. One that is the flip of the other. Another example here is the metric equality. 1 meter is equal to 100 centimeters. Again, we could write that as 100 centimeters over 1 meter, and we can flip it and write it as 1 meter over 100 centimeters. So this is a really good skill to learn how to do, and make sure when you write your conversion factors, write them both ways, because as we start to do conversion calculations, having both written down allows you to figure out, okay, which one do we use in our calculation? Do we use the one where centimeters is on top, or the one where centimeters is on bottom? It depends on what you're converting away from and what you're converting to. So here we have a lot of different equalities. This is a table that, again, I will give to you on the test, so you don't have to memorize equalities, but you do have to know how to go from an equality to the correct conversion factor, right? So writing any of these equalities down as their fraction. So for example, if we want to convert from kilometers to milliliters, then we would want to, that's not liters. I don't know what that is. Let's just say, okay, if we want to convert from quarts to cups, right, we would write this equality as 1 quart over 4 cups, and we also have the conversion factor 4 cups over 1 quart, right? So get used to sort of doing that. So again, we can write metric conversion factors this way. either as 100 centimeters over 1 meter or 1 meter over 100 centimeters. Both are proper conversion factors for the relationship, right? Both represent the same thing, that 1 meter is equal to 100 centimeters. The numbers 101 in this equality, because it's a conversion factor, are both exact numbers here as well. So keep that in mind, right? We're not worried about significant figures here because these are both exact numbers. They're real numbers, right? Because they're an equality, that's what defines them as an exact number. We can write metrics US system conversion factors. So for example, 1 kilogram is the same as 2.2 pounds. So we could write this equality as 2.2 pounds over 1 kilogram, or we can write it as 1 kilogram over 2.2 pounds. Again, both are correct. Both demonstrate that relationship, that if I have 2.2 pounds of caviar, that's the same thing as 1 kilogram of caviar. That's a lot of caviar. That costs a lot of money. So let's get a little bit of practice here. Write the conversion factors from the equality for each of the following. So liters to milliliters, meters to inches, and meters to kilometers. So the first thing you want to look up is what is the equality relationship for each of these units. So again, you would go back to the table here and you would find that relationship. So I'm just going to toggle back here to the first one. So for part A, we want to write or find the equality for liters and milliliters. So if we come back to our table, okay, we can see that here 1 liter is equal to 1,000 milliliters. So that is the equality that I will write down. The conversion factor, therefore, would be written as 1 liter over 1,000 milliliters and 1,000 milliliters over 1 liter. So again, for every equality, you should have 2 conversion factors, one that is the flip of the other. Part B wants us to find the equality between meters and inches. So let's go back to our table and see if it's there. That's going to be length, and yep, there it is, right? 1 meter is equivalent or equal to 39.4 inches. So I would write this down as my equality, and my 2 conversion factors would be 1 meter over 39.4 inches and 39.4 inches over 1 meter. Finally, in part C, we want to relate meters to kilometers or kilometers. So here I would find, all right, 1 kilometer is equal to the same thing as 1,000 meters. So I would write this down as my equality factor for part C. And the 2 conversion factors I should write down is 1 kilometer over 1,000 meters and 1,000 meters over 1 kilometer. All right, so all of those things should give you some more practice in identifying the correct equality and writing down the 2 appropriate conversion factors for that equality. All right, so when we get back into class on Friday or our next class meeting, we will break up into small groups and work on the activity unit conversions, the metric system. Each group should complete this activity and submit their answers as a group with all participant names for full credit. So again, this is what we'll do in our workshop in our next class meeting. All right, so be prepared to do that. For homework, next week, you are going to be working on Chapter 1, Parts 1 and 2 on mastering chemistry. And then for lab next week, we will be getting practice using unit conversions and doing measurements of mass by measuring the density of the various materials in a simulation. So we will meet in lecture in the lecture room for our lab period and work in small groups. We may do this online actually because I think I'm out of town, but I will get with you in class when we meet again in order to clarify that for you guys. All right, so I hope you have a wonderful day. If you have any questions about the in-class assignment and the questions or activities that we did during this lecture, jot them down, shoot me an email, bring it up in class, and I'll be happy to address those questions for you. All right, hope you have a great day. Bye.